step in the expression. We're talking about equivalent expressions today. So we are going to do some work with algebra tiles. Unfortunately, we don't have anything to do at the desk, but we'll use the ones that they have on the book for us. We're going to show you how to rewrite algebraic expressions, and we'll start a little bit on the using distributive property. So this is going to be our focus for today. Your homework today is math. Yeah, guys, you got to get to 60 by next Wednesday. You're not there yet. Get there quickly. So we're giving you a night of homework to do work on math. First, we're going to start with a quick evaluation. We've got 4 problems. We need you guys to work these 4 out. We'll give you guys, this is a little bit more difficult than some of them we've done, especially your division ones. So we'll give you about 3 minutes. Go.
All right. What do I do for the whole number divided by a fraction? A number into by doing what? Putting it over 1. Putting a 1 under it. Now what do I do to divide fractions? Yes, I keep, change, flip. Every time you're dividing fractions, guys, it doesn't change. 5 times 4? 1 times 3? 3. My numerator is bigger than my denominator, so I need to divide. How many times will 3 go into 20? With how many left over? 2 thirds. Any questions? All right, number 2. How do I divide decimals? So first I need to rewrite it. Now what do I do, Savannah? Not yet. You move the decimal points so both of them are not until both of them are whole numbers. Which one has to be a whole number? The one inside. The one on the inside? Outside. The one on the outside. So I'm moving it once. That gives me 6. How many times am I moving the one on the inside? Once. You do it the exact same number of times. And then I move it up into my answer. Then 6 go into 2. 24. How many times? 4. That's 24. Leave 0. So 4/10 is my answer. Number 3. What am I doing first? You're adding. I'm adding. That division bar is working as a grouping symbol. So I need to do my group first. 14 plus 8. 2 stays the same. Now my numerator is larger than my denominator. What do I do? 22 divided by 2 is 11. And number 4. Same thing. I'm adding fractions. What do I do? Okay, so 14 plus 8 is? And my denominator is going to be 2. You do not add your denominator. You have to make sure they are common denominators before you add, and then it stays the same. So 22 divided by 2 is 11. So what do you notice about the answers to 4? Same. But they're the same, but the model, yeah, they are the same. Any questions? Good. Let's look at the next page. Quit talking. The Johnson brothers collect sports gear from their favorite teams. Jaden has a number of jerseys and a number of caps. Jerome has twice as many jerseys as Jaden, but the same number of caps. Josh has 3 times as many jerseys and caps as Jaden. Jack has 4 times as many caps as Jaden, but no jerseys. Okay, so that's a lot of information about the brothers, right? Yeah. So they want you to model it as if you were using algebra tiles. So I'm going to do the first one with you, and then I'm going to let you do the other 3. What does it tell us about Jaden? Has a number of jerseys and caps. Do we know what the number is? No. So how would I model that? And let's look at the directions. It says using X tiles to represent the number of jerseys and Y tiles to represent the number of caps. So what would I put if I don't know the number? X. And all I know is Jaden has X jersey and Y cap. Now, can I use those two things to model the other brother's stuff?
Yes.
Okay, you have about 3 minutes to do that. Go for it. Do not do 2 and 3 yet. Just number 1. You are drawing out the models for the other brothers using that information.
Wait, what is X? What are other ones?
Yeah. How many jerseys would Jerome have?
10.
10, because there are 2 X's, so that's 5 and 5. And how many caps?
7.
Do you see how that could work with any number we put in place of the variable? Okay. I want you to try 2 and 3. 2 says use algebra tiles to model the total amount of jerseys. That's important. And caps that the Johnson brothers have. So you're sketching the model. Then you're writing an algebraic expression that represents the total number of jerseys and caps. So whatever you sketch here, you're going to write it in a problem form. Does that make sense? All right, I'm giving you about 3 minutes to do those 2. Go for it. So if I'm finding the total for all 4 brothers, what am I drawing first? I'm putting them all together. Which one am I doing first? X. How many do I need? 6 X's. Is there 6 X's at the top?
Oh, I'm so little brand looking. They're 9.
X's? No. There's 6. X's? 1, 2, 3, 4, 5, 6. X's for jersey.
Oh, gotcha.
So what am I drawing next for the brothers? 9. 9 Y's. So 1, 2, 3, 4, 6, 7, 8, 9. Make sense? All right, now if I wanted to write this as an expression, what problem would I write to find their total? What does it mean when you have a number and a letter written by each other?
Multiplication.
You don't have to put the multiplication sign because it automatically means to multiply. And your number, which is the coefficient, always goes before your variable. Does that make sense?
Yeah.
Does this problem represent what we drew?
Yeah.
Because we have 6 X's and 9 Y's. Does that make sense? Awesome. Turn the page or look at the next one, whichever. We're on 373.
Oh.
This is like a negative bracket.
Still need the chance.
You just said
Okay, guys. Everyone should have got your highlighters. We got another vocabulary. Called like terms. Like terms are 2 or more terms that have the same variable raised to the same power. Could also include constants. So it doesn't have to be just a variable. Like terms would also include constants.
What are constants again?
Constants and number of boundaries. Okay. Now the coefficients of like terms can be different. That is acceptable. There's nobody considered like terms because they're still talking about the same variable. So we're going to do our exploration of combining like terms with the review of properties of arithmetic and algebra that we're going to use to combine these like terms. We're going to start using the algebra tiles like we just did in the beginning. So on this one, we've got an algebra tile model. We're going to write an addition expression that highlights different tiles in the model. Then, if necessary, combine like terms and write the expression using as few terms as possible. When we combine like terms, that's literally what it does. Combining like terms means putting it in as few terms as possible. So, we haven't really done a whole lot of this, so we're going to go through this first one with you just to show you how this works. So, if I'm going to write this as an addition expression, how many tiles do I have for x squared? 2 of them. So I'm going to write x squared plus x squared because there are 2 of those tiles. Does that make sense? Okay. And how many of the x tiles do I have? 3 of them. So I'm going to write plus x plus x plus x. Then how many of the constant tiles do I have? 4. I'm going to write plus 1 plus 1 plus 1 plus 1. So, does this addition expression represent these tiles? Did I miss anything?
No.
No. So now what we're going to do is this combine like terms piece. Okay? So, in this one, now I'm going to put all of the like terms together. So how many of the x squareds do I have? 2. So I'm now going to rewrite this part of it as 2x squared. How many of the x tiles do I have? 3. So I'm going to rewrite this portion of the expression as 3x. How many of the constants do I have? 4. So I'm going to rewrite this portion of the expression as 4. So what we just did is called combining like terms. We took all the pieces that were the same and put them together. And here's one that often confuses students, so I want to make sure I stress this. Are the x squareds the same as the x? No, they are different. That's why the tiles look different. Okay? That means I cannot combine those. So I can't put the 2x squared with the 3x because those are different. All the x's are the same. That's why I can combine them and say there's 3 of them. The 2x squareds are the same. That's why I can combine them and say there's 2x squared. Does that make sense for everybody? Okay? So now that we've written the addition expression and we've simplified it, now we're ready to answer the next few questions. So I want you guys to go through 2, A, B, and C. And the expression with the fewest terms is this one. So that's really the one you're going to be focusing on. Make sure you do everything that is asked of you. Marking your text. We're talking about it for 3 quarters.
Destiny, Anthony, Rose.
We're talking about marking your text for 3 quarters. I still have a lot of students not doing it, which is really disturbing at this point. Guys, if you will mark your text, it's going to help you be successful because you're going to actually do everything that's being expected of you. Okay? So you only have 3 problems to do. Obviously, this should take about 3 minutes. Go. Okay, how many terms are in your expression with the fewest? In other words, this one, how many terms are there? 3. There are 3 terms. Yeah. How does this relate to the algebra tile model? How does that relate to the tiles? Good. So there are 3 different tiles. Okay. There are 3 different types of tiles. So that's that relationship. So all we're saying is each of those different groups is a different term after I combine them. Okay, what is the greatest exponent in the expression?
2.
Good. If you said squared, I would take that. But really, because they want the greatest exponent specifically, I would have said it just like you did it as 2. The greatest exponent is 2. What is the coefficient of x in the expression? And how does this relate to the tile model? There's 2 parts to our question. What's the coefficient for the x? Is it 2 and 3?
No, it's only asking for it's 3. It's only asking for x, not x squared. It is only 3 because it's not looking for x squared. It's looking for just.
It's just looking for the x. Remember, x squared is different than x. They asked us specifically for the x. So yes, the coefficient is 3. How does that relate to the model?
It's just for the x.
And there are 3 x tiles in the model. Okay. Yep. Are we good on those?
Yes.
Okay. Turn page. Oops. Whoops. Apparently I forgot to read that one. Not for long. So now we're going to change up your level. We've got 3 questions here with a 4th one. You should be able to do all 4 of these. This shouldn't take you long. We've already done several examples at this point. I will say you need to write it initially as your tiles are laid out. So when your initial expression has are laid out before you get to part B, where you're going to rearrange them and put the ones together. Okay? So realize you should have 2 different expressions that are written. We've got about 4 minutes. Go.
A says, write an addition expression that highlights the different tiles in the model. So first of all, how many terms is our expression going to have based on the model? 4. 4. What is my first term? 2x plus
Y squared.
y squared plus
3x.
3x plus
2y squared.
2y squared. Does that make sense?
Yeah.
I have 2 x's, so it's 2x. I have 1y squared. Do I need a 1 when I'm multiplying?
Yeah.
No, because 1 times anything is itself anyway, right? Then what do I have in my third term? 3 x's. And then I have 2 of the y squared. That's all you're doing is numbering them basically. Does that make sense?
Yeah.
All right, then it says rearrange the tiles to combine all like tiles. So, how many x's should I draw?
1. Oh my 5.
5 x's, because those are all alike. And how many y squareds should I draw?
3.
Y squared. I'm really bad at drawing. Y squared and y squared. Yes? So how many terms does my addition expression have now? Say that again.
2.
2. We have 2 terms. What is the first term?
5x.
5x
And then 3y squared.
plus 3y squared. Does that make sense? Any questions about how we did that? Okay. Represent the algebraic expression 3x to the second plus x plus 2 using algebra tiles and sketch a model. How many types of tiles are needed? So what would I draw for the first term? How many times? X squared, x squared, x squared. What about my second term? How many? X, and then my last term. 1 and 1. Yes? So it says how many different types of tiles are needed?
3.
3. We need 3 different types of tiles. No, one and one. Any questions? All right, let's look at, we're skipping a couple pages. Page 378. No, 377, sorry.
Yeah, this one. We're not going to look, in case you guys haven't noticed, we started here at distributive property, and they keep coming back to this. So hopefully you're starting to understand. This is actually mathematically a very important property for us to be able to understand. Distributive property. That's why I have a number on the outside, parentheses and stuff on the inside. So if I look at an expression, 4x plus 8 divided by 4, I can also write that in fraction format, right? Okay? So we're going to start by using these algebra tiles that we've introduced today and start writing it. So if I were to put a model on this, how many x's would I have? 4 x tiles. So I'm going to have 4 x tiles. How many of the individual constant tiles will I have? 8 of them. Because all the constant tiles are always in a 1. So I'm going to have 8 of the 1 tiles.
Oh my god.
And this is quite a bit, but once you understand it, when you can visualize it and understand it, conceptually it should make more sense to you. Okay, so does everybody agree this representation is the same as 4x plus 8? Everybody okay with that? Okay, so our next step, we need to divide our model into 4 equal groups. So I'm going to take I'm just going to sketch it on here. What did we end up doing?
1.
There's 1, 2, 3, 4 groups. Would that work? Okay. So I now have 4 equal groups. What do I have inside of each group?
1 x 2 1.
1x and 2 1s. So if I were to write an expression to represent each group from my sketch, I would say each group has 1x and 2 1s. Everybody okay with that? Anybody not see it? So everybody sees it. Okay? Now, verify that we created equal groups by multiplying your expression for part C by 4. So now I'm going to take this expression that I just did, part C, and I'm going to multiply that by 4. Is everybody okay with that?
Yeah.
This right here is distributive property. I've got a number on the outside, two or more numbers on the inside. Who remembers our first step for distributing? No, not for distributing. That's order of operations. Dominic was right. If it was order of operations, you in the parentheses first. But distributive property is a little different. Then, and then I do what? Okay, I'm hoping this is what you're saying. I was looking for the word arrows because we've told you repeatedly, draw an arrow to each of the numbers to make sure that you're doing it right. So then, as Savannah said, I'm not taking that number and multiplying by each of the inside. So 4 times x is going to give me what? 4x. I just write the number, or the operation plus, then I do 4 times 2 and I get 8. So is that equal to 4x plus 8? You see why? Does everybody understand what we did in our steps? Yeah. Any questions on it? No. Okay, good. Let's go to our next page. 30 seconds. So, all you have to do is put the 2 in each piece.
man. Sounds like nobody. That was